Picture the universe in its grandest scale, a breathtaking tapestry woven from countless galaxies, swirling nebulae, and the silent, dark voids in between. For centuries, we've mapped the stars, measured their light, and theorized about the fundamental stuff that holds everything together. We thought we had a pretty good inventory. But then, astronomers made a discovery that sent shockwaves through the scientific community, a cosmic accounting error of unimaginable proportions. It turns out about half of the normal matter in the universe, the kind that makes up you, me, planets, and stars, is simply missing. It vanished without a trace, leaving behind one of the most profound and puzzling mysteries in all of modern astrophysics. This isn't some exotic dark matter we're talking about. This is the ordinary, tangible stuff of creation, and half of it has gone AWOL. Welcome to the greatest cosmic detective story of our time, the case of the missing baryons. So, what are these baryons? In simple terms, they are the building blocks of the visible universe. Protons and neutrons, the particles that form the nuclei of every atom in your body, in the air you breathe, in the screen you're looking at right now, are baryons. They are the substance of everything we can see and touch. For decades, our most precise calculations, based on the afterglow of the Big Bang, told us exactly how much of this baryonic matter should be out there. Yet, when we added up all the stars, galaxies, and gas clouds we could observe, we came up staggeringly short. A whopping 50% was just gone. This isn't a small miscalculation. It's a gaping hole in our understanding of the cosmos, a silent, invisible sector of reality that holds the key to the universe's true structure. This is where our journey begins, a thrilling expedition into the vast, uncharted territories between galaxies. We are not just passive observers in this mystery, we are detectives on the trail of the universe's biggest secret. And today, we are going to follow the evidence. Astronomers haven't been idle. They've been assembling clues piece by piece, using the most powerful telescopes and ingenious methods to hunt for this lost matter. They have compiled 25 tantalizing clues, hints that point to where this missing half of the universe might be hiding. These clues take us on an adventure through the cosmic web, into the superheated filaments of gas that stretch between galaxies and force us to reconsider everything we thought we knew about the space between the stars. So get ready to join the search as we unpack the evidence, explore the theories, and follow these 25 incredible clues to solve the mystery of the missing baryons. The very first clue in our investigation is perhaps the most startling one because it reveals the sheer scale of the problem. It all begins with a cosmic ledger, a balance sheet for the entire universe. On one side of this ledger, we have the total amount of normal matter that should exist, a number predicted by two of the most trusted pillars of modern cosmology. The first is Big Bang nucleosynthesis, the process that forged the first atomic nuclei in the universe's fiery infancy, just minutes after its birth. The conditions during that brief, intense period determined the exact proportions of hydrogen, helium, and a tiny bit of lithium that were created. And those proportions tell us precisely how many baryons, how many protons and neutrons were present at the dawn of time. The second, even more precise measurement comes from the cosmic microwave background, that faint afterglow of the Big Bang that fills all of space. By studying the tiny temperature fluctuations in this ancient light, we can read the blueprint of the early universe and get an incredibly accurate census of its total baryon content. Both of these methods, operating from completely different physical principles, agree perfectly. They give us the definitive starting budget for all the normal matter in the cosmos. Now, let's look at the other side of the ledger, the present-day universe. This is where astronomers began their inventory, meticulously counting up everything they could see. They tallied the stars in countless galaxies, they measured the vast clouds of cold gas within those galaxies, and they accounted for the hot plasma in galaxy clusters. It was a monumental task of cosmic accounting, but when they added it all up, the final number was a shock. They found only about half of the Baryons that the early universe's ledger said should be here. Not a small rounding error, but a staggering 30 to 50% shortfall. Imagine building a house with a detailed blueprint and a precise list of materials. You use exactly half the bricks, half the lumber, and half the wiring, and then you look at the finished structure and it appears complete. You'd be utterly baffled, wondering where the rest of the materials are hidden. That's the exact predicament cosmologists found themselves in. The universe, according to our observations, seemed to be only half built with the normal matter we knew should exist. This mismatch isn't just a minor puzzle, it's a fundamental challenge to our understanding of cosmic evolution. It forces us to ask a critical question. If the matter was there at the beginning and it can't be destroyed, then where did it go? The only possible answer is that it must be hiding in plain sight, in a form or a place we hadn't been able to see. This initial clue, the cosmic inventory mismatch, sets the stage for our entire investigation. It transforms the vast, seemingly empty spaces between galaxies from mere voids into potential crime scenes, the most likely hiding places for a universe's worth of missing material. So if the cosmic ledger shows a massive shortfall, our investigation immediately turns to the most obvious suspect, the vast, seemingly empty spaces between galaxies. This leads us directly to our second clue, the warm-hot intergalactic medium, or WHIM. This isn't a cold, empty void as we once imagined. Think of it instead as a cosmic spider's web, but one made of unimaginably hot gas. This web is the scaffolding of the universe, a network of filaments that connects clusters and superclusters of galaxies. And according to the leading theory, this is where the missing 50% of all normal matter has been hiding all along. The sheer scale of this structure is almost beyond comprehension. If you could see it, you would see that galaxies are not isolated islands in a black sea, but merely the densest, brightest knots in a sprawling, interconnected cosmic metropolis, with these gaseous filaments acting as the highways and bridges between them. The material in these filaments is what we call the WHIM, and it's the prime candidate for solving our mystery. Now, you might be wondering, if this gas is everywhere, why has it been so incredibly difficult to find? The answer lies in its unique and almost perfectly elusive properties. This isn't the kind of cold, dense gas we find inside galaxies that readily forms stars and glows with visible light. The WHIM is, as its name suggests, both warm, hot, and extremely diffuse. We're talking about temperatures ranging from hundreds of thousands to several million degrees Celsius. At these tremendous temperatures, the atoms are ripped apart, electrons are stripped from their nuclei, creating a thin, electrified soup known as a plasma. This state of matter is the key to its invisibility cloak. Because the atoms are ionized, they don't absorb or emit light in the specific, narrow wavelengths that our traditional optical telescopes are designed to detect. They don't produce the familiar spectral fingerprints that cold gas does. Furthermore, this gas presents a classic Goldilocks problem for astronomers. While it is hot, it's often not quite hot and dense enough to shine brightly in X-rays, which is how we typically spot million-degree plasmas, like the vast reservoirs of gas enveloping galaxy clusters. The WHIM is far more tenuous. Imagine trying to see the heat rising from a single candle from a mile away, while right in front of you is a blazing bonfire. That's the challenge of spotting the faint X-ray glow of the WHIM against the brighter background of the universe. It's too energetic to be seen in visible light, yet too faint and spread out to be an obvious X-ray source. It exists in a perceptual blind spot, a perfect cosmic hiding spot that has allowed it to evade detection for decades, silently containing what could be the largest reservoir of ordinary matter in the entire cosmos. But if the WHIM is so perfectly invisible, how can we possibly hope to find it? This is where our investigation turns to one of the most ingenious and indirect methods in the astronomer's toolkit, our third clue, the Sunyaev-Zeldovich effect. To understand this, we need to go back to that ancient afterglow of the Big Bang, the cosmic microwave background, which we mentioned earlier as our cosmic ledger. This radiation is the oldest light in the universe, a nearly uniform bath of photons that has been traveling across space for over 13 billion years. It's the foundation upon which the entire cosmos is painted. Now, imagine this pristine, ancient light, after traveling for eons, finally entering a region of space that isn't empty at all, but is filled with the superheated, ionized gas of the WHIM. As these CMB photons pass through this sea of incredibly hot electrons, something remarkable happens. The electrons, buzzing with immense thermal energy, don't just let the photons pass by untouched. They interact with them through a process called inverse Compton scattering, giving the photons a tiny but measurable boost in energy. The result is a subtle distortion, a kind of spectral fingerprint left on the background radiation. In the specific direction of a vast cloud of hot gas, the cosmic microwave background doesn't look quite the same. At the lower frequencies where the CMB is brightest, there's a slight shadow or a dip in its intensity. Meanwhile, at higher frequencies, there's a corresponding increase in brightness. This dual signature is the telltale mark of the Sunyaev-Zeldovich effect. It's as if the universe has provided us with a perfect, uniform canvas, and any bump or wrinkle in that canvas reveals something about the material that's in front of it. We aren't seeing the hot gas itself, we're seeing its ghostly impression, its shadow cast upon the most distant screen imaginable. This makes the AZ effect an exquisitely powerful tool because its strength doesn't diminish with distance. Whether the cloud of gas is 1 billion light-years away or 10 billion light-years away, the distortion it imprints on the CMB remains just as detectable, allowing us to probe the large-scale structure of the universe to incredible depths. To make this work, we need a way to pinpoint where to look, and nature provides us with the perfect signposts: massive galaxy clusters. These colossal structures, containing thousands of galaxies, are embedded within even larger atmospheres of million-degree gas. They are the brightest beacons in the cosmic web, and crucially, they are often found at the intersections of the very filaments of the WHIM that we're trying to map. Astronomers use these clusters as natural backlights. By pointing our most sensitive radio and microwave telescopes at them, we are not just looking at the cluster itself, but also peering through the entire column of space along our line of sight. The total Sunyaev-Zeldovich signal we measure is an integrated effect. It adds up the pressure from every single hot electron that the CMB photons encountered on their journey from the edge of the observable universe to our telescopes. This means that the signal isn't just coming from the dense, hot gas in the central cluster. A significant part of it can come from the more diffuse and far more widespread gas in the intergalactic filaments that the cluster is connected to. By carefully analyzing this signal and comparing it with what we'd expect from the cluster alone, astronomers can hunt for that extra diffuse component. They are essentially measuring the total electron pressure in a giant cylinder of space stretching across billions of light-years. When they find an SZ signal that is stronger than what the visible cluster gas can account for, it points directly to the presence of the WHIM in the surrounding cosmic web. It's like hearing an echo in a canyon that is louder than the original shout, telling you that there are more rock walls and hidden crevices contributing to the sound than you can immediately see. This method has already provided some of the most compelling, albeit indirect, evidence for the missing baryons. By surveying thousands of clusters and carefully mapping the SZ effect around them, we are beginning to trace the outline of the cosmic web itself, finally making the invisible architecture of our universe visible and weighing the long-lost matter that has been hiding within it all along. While the Sunyaev-Zeldovich effect gives us a powerful, wide-angle view of the cosmic web, it's like seeing the silhouette of a forest from a distance. To truly understand what the trees are made of, we need to get closer and analyze their chemical composition. This brings us to our fourth crucial clue, a method that acts as the universe's own forensic lab, the detection of X-ray absorption lines. Here, astronomers turn from using the cosmic microwave background as a backlight to employing the most brilliant and distant beacons in the universe, quasars. These are not stars in the conventional sense, but the incredibly luminous cores of active galaxies, powered by supermassive black holes greedily consuming material. As matter spirals into the black hole's gravitational well, it heats up to phenomenal temperatures, releasing a torrent of radiation across the entire electromagnetic spectrum, including a fierce, concentrated beam of X-rays. Think of a quasar as the ultimate cosmic flashlight, a searchlight so powerful it can illuminate the entirety of intergalactic space between its distant location and our telescopes. The real detective work begins when we analyze this brilliant X-ray light with instruments like the XMM Newton and Chandra observatories. As the quasar's light travels across billions of light years towards us, it doesn't journey through a perfect vacuum. It passes through the vast, diffuse filaments of the warm, hot intergalactic medium. Remember, the WHIM is a plasma of ionized atoms, oxygen, nitrogen, carbon, and neon that have been stripped of some or most of their electrons by the intense heat. When a quasar's X-ray light, which contains a continuous spectrum of energies, encounters these ions, a specific and telling interaction occurs. An atom can absorb a photon of light, but only if that photon has exactly the right energy to boost one of its remaining electrons into a higher energy level. For highly ionized oxygen that has lost 5 of its 8 electrons, known as OVI, this absorption happens at a very specific, high-energy wavelength in the X-ray part of the spectrum. So, when astronomers point an X-ray telescope at a distant quasar and spread its light out into a spectrum, they don't see a perfectly smooth curve. Instead, they search for the telltale, sharp dips in the data. These are the absorption lines. Each dip is a direct fingerprint, a signature that says, "A cloud of million-degree ionized oxygen was here." It's as if we're analyzing a beam of pure white light after it has passed through a specific gas and finding a unique, dark line in the resulting rainbow that identifies that gas beyond any doubt. The beauty of this method is its precision. Not only does it confirm the presence of the hot gas, but the specific wavelength of the absorption line tells us which element we're detecting and its level of ionization, which in turn reveals the temperature of the gas. The depth of the dip gives us information about the density of the material. It's a phenomenally detailed way to study a substance that is otherwise completely invisible to our eyes. The hunt for these ghostly signatures has been a primary goal for X-ray observatories for years, and the results have been groundbreaking, though incredibly challenging to obtain. The signals are exceptionally faint because the WHIM is so diffuse. It's like trying to detect the faintest haze in the atmosphere by studying the light from a single, distant star. You need immense sensitivity and patience. Missions like XMM Newton, with its large collecting area, are perfect for gathering as much of this precious light as possible, while Chandra's exquisite angular resolution helps pinpoint the exact location of the quasars. After years of searching and analyzing countless quasar spectra, astronomers began to find them, those predicted subtle dips corresponding to highly ionized oxygen and other elements. In several landmark studies, they identified absorption systems that could not be attributed to the quasar itself or to our own galaxy. The only possible source was the vast cosmic web stretching across the immense void between galaxies. They were literally seeing the shadows cast by the missing Baryons. Each successful detection is like finding a single, specific tree in the vast forest we saw from afar with the SZ effect. By finding these absorption lines in the light of multiple quasars, astronomers can start to build a map, they can determine not just that the WHIM exists, but where its densest filaments are located and how they connect the large-scale structures of the universe. This method provides the tangible, chemical proof that the theoretical framework of the cosmic web is correct and that it is indeed saturated with the long-sought missing matter. It transforms the WHIM from a compelling theoretical idea into an observed physical reality, one whose properties we can now measure and study directly, finally bringing the hidden half of the ordinary universe out of the shadows and into the light of scientific understanding. Now, while X-ray absorption lines give us a direct look at the hottest components of the cosmic web, there is another, even more prolific forest of clues that astronomers have been studying for decades. This brings us to our fifth clue, a phenomenon with a beautifully evocative name, the Lyman Alpha Forest. To understand this, we once again turn to the brilliant light of distant quasars, but this time we shift our gaze from high-energy X-rays down to the ultraviolet part of the spectrum. As this ultraviolet light journeys across the universe, it doesn't just pass through the million-degree gas. It also travels through countless clouds of much cooler, neutral hydrogen gas that are strewn along the vast expanses of intergalactic space. These aren't dense clouds like the ones in our own galaxy that form stars. They are wispy, primordial structures, the basic scaffolding upon which galaxies themselves eventually formed. When a photon from the quasar with the exact right energy corresponding to the Lyman alpha transition of hydrogen encounters one of these neutral hydrogen clouds, it gets absorbed. The atom soaks up the photon, and this creates a very specific, sharp dip in the quasar's otherwise smooth ultraviolet spectrum. Now, here's where the forest part comes in. The quasar's light isn't just passing through one or two of these clouds. It's traversing billions of light years, intersecting with thousands upon thousands of them. Each cloud, depending on its distance from us, is moving away at a different velocity due to the expansion of the universe. Because of the Doppler effect, this motion shifts the absorption line to a slightly different wavelength for every single cloud. The final result, when we spread the quasar's light out into a spectrum, is breathtaking. Instead of a clean, continuous curve, we see a veritable forest of absorption lines, a dense thicket of dips and troughs crowding the spectrum. Each one of those lines is a unique tree, representing a single cloud of hydrogen at a specific location in the cosmic web. This Lyman alpha forest is far more than just a curious sight. It is one of the most powerful tools in cosmology. Think of it as a natural cosmic thermometer and barometer spread across the entire universe. By analyzing the precise placement, width, and depth of these countless absorption lines, astronomers can create an incredibly detailed map of the distribution of matter along this specific line of sight. They can measure the density of the gas in these clouds, determine their temperature, and trace the underlying gravitational framework of the dark matter that draws this gas into filaments and sheets. The forest reveals the cosmic web in stunning detail, but in a cooler, more neutral form. So, what does this have to do with our search for the missing hot baryons? The connection is both subtle and profound. These neutral hydrogen clouds don't exist in isolation. They are believed to be embedded within and pressurized by the far more extensive and much hotter envelope of the WHIM. The cooler clouds are like the visible foam on the surface of a deep, hot ocean. They are the parts we can easily see, but their very existence and distribution are dictated by the immense, invisible body of hot plasma surrounding them. The properties of the Lyman alpha forest provide crucial, indirect evidence for this surrounding hot gas. For instance, the widths of the absorption lines tell us about the temperature and turbulence within the clouds. Broader lines can indicate the clouds are being heated and stirred up, likely by the intense thermal pressure from the million-degree WHIM that is bathing them. Furthermore, sophisticated computer simulations of the universe's structure formation show that the specific patterns we see in the Lyman alpha forest, how clustered the lines are. their statistical distribution can only be reproduced if a massive amount of hot, ionized gas is present in the spaces between these neutral clouds. The forest, in essence, acts as a tracer. By studying the trees, we can infer the properties of the soil and the climate in which the entire forest grows. It provides a compelling statistical argument that the vast reservoirs of the warm, hot intergalactic medium must be there, filling the voids and shaping the environment, thereby accounting for a significant portion of the baryons that our direct inventories had missed for so long. It's a classic case of seeing the effect to understand the cause, using the most abundant element in the universe to illuminate the shadowy presence of its hotter, invisible counterpart. Moving from the sprawling forest of hydrogen clues, our investigation sharpens its focus to hunt for specific chemical fingerprints, the kind that can only be left by the most extreme environments in the cosmic web. This leads us to our sixth clue, and it involves two of the most sought-after signatures in all of astrophysics: absorption lines from highly ionized oxygen, specifically O-7 and O-8. Think of oxygen as a cosmic workhorse. It's one of the most abundant elements forged in the hearts of stars and scattered throughout the universe by supernova explosions. Because it's so common, it makes for a perfect tracer. But to use it as evidence for the WHIM, we need to find it in a very specific and very dramatic state. An atom of oxygen normally has 8 electrons buzzing around its nucleus. O-7 is an oxygen atom that has been through the cosmic ringer, having lost 7 of those 8 electrons. O-8 is even more extreme. It's been stripped completely bare, a naked oxygen nucleus with no electrons left at all. Creating atoms in these states requires a tremendous amount of energy, which means an environment of staggering heat. We're talking about gas heated to temperatures between 1 million and 10 million degrees Celsius. This is precisely the temperature range predicted for the densest and hottest parts of the warm, hot intergalactic medium. So, when astronomers detect the spectral signatures of O-7 or O-8 in the light of a distant quasar, it's like finding a smoking gun. It's direct, incontrovertible proof that the quasar's light has passed through a region of space filled with gas at exactly the million-degree temperatures that define the missing Baryon reservoir. The absorption lines these ions create are found in the soft X-ray part of the spectrum, and their specific wavelengths are like unique barcodes, immediately identifying not only the element but its exact level of ionization, locking in the temperature of the gas with remarkable precision. The hunt for these specific barcodes has been one of the most compelling and at times most frustrating chapters in the search for the missing matter. The theory is perfectly clear. If the WHIM is real and it contains a large portion of the universe's baryons, then its filamentary structures should be saturated with O-7 and O-8. We should be able to point our most powerful X-ray telescopes, like XMM Newton and Chandra, at a bright quasar and see a whole series of these absorption lines, each one corresponding to a different filament of the cosmic web that the light has pierced on its long journey to Earth. In several landmark observations, that is exactly what astronomers have seen. They have identified clear, sharp dips in quasar spectra that match the predicted wavelengths for O-7 and O-8. These detections are monumental. They are some of the most direct pieces of evidence we have that the theoretical picture of the hot cosmic web is correct. It's the difference between inferring a suspect was at a crime scene and actually finding their fingerprint on the weapon. However, the story is not as simple as finding a fingerprint in a well-lit room. The challenge is that these signals are incredibly, almost maddeningly faint. The WHIM is not a dense, solid wall of hot gas. It's an ethereal, wispy veil. The amount of this highly ionized oxygen in any given line of sight is minuscule, meaning the resulting absorption lines are exceedingly shallow. Detecting them is like trying to hear a single, quiet whisper in a roaring concert hall. It requires not only incredibly sensitive instruments, but also a tremendous amount of observing time, often requiring these great observatories to stare at a single quasar for days on end just to collect enough X-ray photons to produce a usable spectrum. And even then, the results can be ambiguous, with the potential for instrumental noise or other astrophysical contaminants to mimic the signal we're so desperately seeking. This leads to the second major hurdle: inconsistency. While we have beautiful textbook detections of O7 and O8 along some lines of sight, other seemingly identical quasar observations come up empty. This patchy, hit-or-miss nature of the detections is in itself a crucial piece of the puzzle. It tells us that the WHIM is not a uniform fog evenly spread throughout space. Instead, it is lumpy and highly structured, concentrated into specific filaments and sheets. Whether you see it or not depends entirely on whether your particular line of sight to a quasar happens to skim through one of these dense knots in the cosmic web. It's like looking through a vast, tangled jungle from above. Some sightlines will pass through several thick branches, while others might pass through mostly open air. This inconsistency, while frustrating for getting a simple, clean answer, actually paints a more realistic and dynamic picture of the universe's large-scale structure. It confirms that the missing baryons aren't missing at all. They are just meticulously hidden within an intricate, hot, and elusive architectural framework that we are only now beginning to map, one precious X-ray photon at a time. One of the most dramatic and energetic processes in the universe might also be a primary accomplice in the great cosmic disappearance. To understand how half the universe's normal matter ended up scattered across the voids, we must turn our attention to the very engines that drive galactic evolution, galactic winds. These are not gentle breezes but colossal, superheated outflows erupting from galaxies, carrying vast quantities of gas and heavy elements and blasting them deep into intergalactic space. There are two primary powerhouses behind these cosmic gusts. The first originates from regions of intense star formation. In stellar nurseries, massive stars live fast and die young, ending their short lives in spectacular supernova explosions. When thousands of these explosions occur in quick succession, they create a collective shockwave that can blow the surrounding gas clean out of the galaxy's gravitational grip, like a constant, powerful wind generated by a non-stop fireworks display. The second, and often even more violent, source of these outflows comes from the very heart of active galaxies. When a supermassive black hole is actively feeding, it doesn't just swallow matter quietly. The intense friction and magnetic fields around it can launch jets and winds of material moving at a significant fraction of the speed of light. These active galactic nuclei, or AN, can generate winds so powerful they not only push gas out of their host galaxy, but can also completely shut down star formation across vast regions, putting the brakes on the galaxy's own growth. Both of these processes, starburst-driven winds and AGN outflows, act as cosmic conveyor belts. They are constantly working to transport the very stuff of galaxies, the baryons in the form of gas and the heavy elements forged in stars, out of the relatively dense galactic disks and into the much more diffuse surroundings. This isn't a trivial leak, it's a systematic expulsion of material on a truly epic scale, a fundamental part of how galaxies interact with and shape their environment. So, what happens to all this ejected material? This is where our search for the missing baryons converges beautifully with the story of galactic winds. The gas that gets blown out doesn't just vanish into nothingness. Instead, it becomes a primary source of enrichment and heating for the warm, hot intergalactic medium. As these energetic winds crash into the cooler, more tenuous gas that already exists in the spaces between galaxies, they inject enormous amounts of energy. This collision heats the gas to those perfect hiding temperatures of millions of degrees, effectively cooking the baryons into the hot, ionized plasma state that makes up the WHIM. Furthermore, these winds are not just made of pure hydrogen and helium. They carry with them the heavy elements, the oxygen, carbon, and iron forged in the nuclear furnaces of stars and scattered by supernova. This is a crucial piece of the puzzle because it directly explains the chemical fingerprints we've been searching for. When we detect those highly ionized oxygen absorption lines in quasar spectra, we are likely seeing the scattered remains of ancient stellar explosions, the pollution from generations of stars that was violently ejected from its home galaxy and dispersed throughout the cosmic web. This process effectively completes a cosmic cycle of hiding. Galactic winds take baryons that we could relatively easily observe when they were cold and concentrated inside galaxies, and they pump them into a state and a location where they become extraordinarily difficult to detect. The winds heat and ionize the gas, rendering it invisible to optical telescopes. They spread it out over such immense volumes that its X-ray glow becomes faint and elusive. And by enriching the intergalactic medium with metals, they provide the very tracers we now use to find it, but only with our most sensitive and dedicated observations. In this light, the missing baryons aren't so much lost as they are redistributed. They have been systematically moved from the bright, visible cities of the universe, the galaxies, and into the sprawling, invisible suburbs and countryside of the cosmic web, hidden in plain sight by the very physical processes that govern how galaxies live and die. Building on this idea of galactic winds redistributing matter, we must now zoom out to the grandest scale imaginable to see the final destination for all this ejected material. This brings us to our eighth clue, and it requires a fundamental shift in how we picture the cosmos. Forget the classic image of isolated galaxies drifting in an empty black void. Instead, envision the universe as a colossal, three-dimensional spider's web, an intricate architecture known as the cosmic web. This isn't just a poetic metaphor, it's the prevailing theory of cosmic structure formation, and it provides the ultimate hiding place for the missing baryons. The invisible threads of this web are woven not from normal matter, but from the mysterious gravitational influence of dark matter. This dark matter forms an unseen skeleton, a scaffolding of long, thin filaments that stretch across billions of light years, connecting the densest hubs of the universe, the massive clusters of galaxies like cities linked by an interstellar highway system. The normal matter, the baryons that make up everything we see, simply follows the gravitational blueprint laid down by this dark matter framework. As the universe evolved, the pull of gravity drew ordinary matter, primarily hydrogen and helium gas, into these vast filamentary channels. Think of it like water vapor condensing onto the intricate strands of a spider web on a dewy morning. The gas naturally flows into and settles along these pre-existing dark matter threads. The galaxies we observe, including our own Milky Way, are not scattered randomly. They are primarily found at the intersections of these filaments, the dense knots where multiple strands of the cosmic web meet, creating a gravitational well deep enough to trigger galaxy formation. So, when you look at a three-dimensional map of the universe showing the positions of millions of galaxies, you are essentially looking at the illuminated nodes of this immense dark structure. The glowing galaxies are just the glittering tips of a much larger, mostly invisible iceberg. This is where our missing baryons come into the picture with stunning clarity. According to the most sophisticated computer simulations of the universe, the vast majority of the normal matter that is not locked inside stars and galaxies should reside within these very filaments. They are not empty conduits, they are the universe's primary reservoirs for baryonic matter. The gas within these filaments is the warm, hot intergalactic medium in its natural habitat. It has been gravitationally pulled into these structures and further heated by the immense shock waves generated as matter flowed along them and collapsed into the web over billions of years. The sheer volume of space occupied by these filaments is staggering. While galaxies and clusters are relatively compact, the web of filaments fills the majority of the cosmic volume. This means that even though the gas inside any given cubic light year of a filament is incredibly diffuse, The cumulative mass from the sheer enormity of this network adds up to an astronomical figure, precisely the 50% of baryons that had eluded our detection. Visualizing this helps us understand why it has been so difficult to find. Imagine you're trying to map a cloud from the inside. If you're standing right in the middle of it, all you see is a uniform, faint mist. It's only when you get far enough away to see the entire cloud structure that you can discern its distinct shape and boundaries. We are inside the cosmic web, making it nearly impossible to see its full, fibrous structure directly. The filaments themselves are immense but also incredibly thin relative to their length. A single filament might be millions of light years long, but only a few million light years in diameter. Trying to observe one is like trying to see a single thread of a spider's web from 100 feet away. We lack the perspective to see the whole tapestry at once, and the individual threads are too faint and wispy to spot easily. Our search, therefore, relies on the indirect methods we've already discussed: the Sunyaev-Zeldovich effect that feels the pressure of the hot electrons, and the absorption lines that reveal the chemical makeup of the gas as the light of distant quasars skims through these cosmic threads. The cosmic web filament theory provides the grand, unifying framework. It tells us exactly where to look, transforming the mystery from a search for a ghost in a vast, empty room into a targeted hunt for the specific, albeit elusive, architecture that forms the backbone of the cosmos itself. But just when we think we have a handle on the Sunyaev-Zeldovich effect, the universe reveals another layer of subtlety, another tool for our detective kit. We've seen how the thermal SZ effect acts as a cosmic thermometer, measuring the intense heat of electrons. Now we turn to a more elusive but equally powerful phenomenon, our ninth clue, the kinetic Sunyaev-Zeldovich effect. While the thermal version is all about temperature, the kinetic version is all about motion. Imagine the cosmic microwave background as a steady, gentle rain falling straight down. The thermal SZ effect is like this rain passing through a hot sauna. The hot, buzzing air molecules give the raindrops a random energy boost, warming them up. The kinetic SZ effect, however, is like that same rain falling through a moving mist. If the entire cloud of mist is drifting sideways, it will give the raindrops a slight, collective shove in that direction, changing their apparent path without necessarily heating them up. In cosmic terms, this moving mist is a vast cloud of electrons that has a net velocity relative to the smooth background of the CMB. This isn't the random, jittery motion from heat, but a coherent bulk flow. The entire cloud is moving in one direction, perhaps being pulled by the immense gravitational tug of a nearby supercluster or flowing along a filament of the cosmic web. As the CMB photons scatter off these moving electrons, they experience a Doppler shift. If the cloud is moving toward us, the photons get a slight blue shift, appearing ever so slightly warmer. If the cloud is moving away, the photons get a red shift, appearing marginally cooler. The key distinction is profound. The kinetic SZ signal depends only on the density of the electrons and their bulk velocity, not on their temperature. This makes it an entirely different kind of probe. The thermal SZ effect is brilliant for finding the hottest, most energetic plasma, like the gas in the hearts of galaxy clusters. But the kinetic effect is sensitive to any dense cloud of electrons, even if it's relatively cool. This is a game changer for hunting the WHIM, because not all of it is at millions of degrees. Some filaments, especially the smaller or more distant ones, could be far cooler and would be completely invisible to the thermal SZ method. Detecting this signal, however, is like trying to hear a pin drop in a hurricane. The kinetic SZ imprint on the CMB is incredibly faint, about 10 times weaker than its thermal counterpart. The temperature change it creates is minuscule, a fluctuation of mere millionths of a degree. To make matters more complex, the kinetic signature looks almost identical to the primordial fluctuations that are naturally part of the CMB itself. It's the ultimate cosmic camouflage, so how do astronomers possibly hope to see it? The answer lies in a clever strategy of cross-correlation. they don't just look at the CMB alone, they combine it with other maps of the universe's structure. For instance, they take ultra-precise CMB maps from observatories like the Atacama Cosmology Telescope or the South Pole Telescope and overlay them with three-dimensional maps of galaxy positions from massive surveys. Galaxies trace out the densest regions of the cosmic web, the very knots and filaments where we expect these bulk flows of electrons to be occurring. By statistically comparing these two maps, astronomers can search for a telltale pattern. They look for places where the subtle cold or hot spots in the CMB align precisely with the known velocities of galaxy clusters and filaments. When they find a consistent correlation, a slight CMB dimming that always appears when a massive structure is moving away from us or a brightening when it's moving toward us, they can isolate the kinetic SZ signal from the background noise. It's a statistical whisper that, when gathered from thousands of different clusters and filaments, becomes a shout. This technique is allowing us to probe the electron density in regions previously beyond our reach, directly weighing the baryonic content of the cosmic web's architecture. It provides a crucial, independent line of evidence that complements the thermal SZ and X-ray absorption methods, helping us to build a complete census of the missing matter, regardless of its temperature, by sensing its collective motion through the vastness of space. Facing the challenge of these incredibly faint and often inconsistent individual signals, astronomers had to get creative, turning to a powerful statistical technique that lies at the heart of modern astrophysics: stacking. Think of it like trying to listen to a conversation across a crowded, noisy room. If you only listen for a single second, you might not hear anything intelligible. But if you record hours of that background chatter and then use a computer to isolate and amplify just the sound of a specific person's voice from all the different moments they spoke, you can suddenly piece together entire sentences. That's precisely what stacking does for the hunt for the missing baryons. Instead of relying on a single, perfect, and often elusive detection from one quasar or one galaxy cluster, astronomers combine the data from hundreds or even thousands of similar systems. They take all those individual, noisy observations where the signal from the WHIM is too weak to be seen on its own, and they digitally layer them on top of one another, perfectly aligned. The magic of this process is how it treats the signal versus the noise. The specific signature we're looking for, whether it's a faint X-ray absorption line at a specific wavelength or a subtle SZ effect imprint, is roughly the same in every stacked system. It's a coherent pattern. The random noise from the instruments, however, and the unrelated astrophysical background is different in every single observation. When you stack or co-add all these datasets, the coherent signal adds up linearly. If you double the number of observations, you double the strength of the real signal. The noise, being random, adds up much more slowly. It increases only as the square root of the number of observations. So, with enough data points, the signal-to-noise ratio grows steadily, and what was once an invisible whisper beneath the static gradually emerges as a clear, detectable voice. It's a way of letting the universe's faintest structures speak in unison, their collective voice finally loud enough for our telescopes to hear. This approach has been instrumental in building the statistical case for the warm-hot intergalactic medium. For example, astronomers have applied stacking to vast catalogs of quasar spectra. They select thousands of quasars and extract the X-ray or ultraviolet spectrum for each one. Then they shift each spectrum so that the expected rest frame wavelength of a specific absorption line, like that from O-7, lines up perfectly in all of them. When they create a single master spectrum by averaging all these individual ones together, a remarkable thing often appears: a clear, statistically significant absorption dip right at the predicted wavelength, a dip that was completely absent in almost every single spectrum on its own. This isn't a detection of one specific filament, it's a detection of the average properties of the entire cosmic web. It tells us that, on average, the sight line to any distant quasar will pass through a certain amount of this highly ionized oxygen, confirming that the WHIM is a pervasive, universal component of the large-scale structure. The same powerful logic applies to the Sunyaev-Zeldovich effect. Instead of studying one cluster in isolation, astronomers create stacks based on the properties of thousands of clusters, grouping them by mass, by distance, or by their environment. They then take the CMB data around all the clusters in a given group and stack it, looking for a consistent SZ signature that extends far beyond the cluster's known boundaries. This has allowed them to map the average pressure profile of the gas surrounding these massive structures, directly revealing the hot, diffuse envelope of the WHIM that connects them to the cosmic web. These stacked SZ maps show a gentle, fading halo of electron pressure that stretches for millions of light years into the empty intercluster space, a direct measurement of the vast reservoir of hot gas that simple galaxy counts had missed. Through the patient, powerful act of stacking, the faint ghost of the missing baryons materializes not as a single entity, but as a statistical certainty, proving that our inability to see them individually was never a sign of their absence, but only a limitation of our methods. While our investigation has largely focused on the grand filaments connecting massive clusters, the cosmic web has a finer, more intricate structure, one that exists on a much more local scale. This brings us to our 11th clue, and it asks us to zoom in from the vast superclusters down to the galactic neighborhoods we call galaxy groups. These are the most common gatherings of galaxies in the universe, small collections of a few dozen galaxies or less, held together by their mutual gravity. Our own Milky Way is part of one, the charmingly named local group, which also includes the Andromeda Galaxy, the Triangulum Galaxy, and over 50 smaller dwarf galaxies. These groups are the fundamental building blocks of cosmic structure, far more numerous than the immense clusters we often see in dramatic telescope images. And just like their larger cousins, they are surrounded by their own atmosphere of hot gas, known as the intragroup medium. The crucial question is, how much of the universe's missing normal matter could be hiding in these countless smaller systems? The answer appears to be a significant amount. The intragroup medium is theorized to be a major reservoir of warm hot gas, but it presents a unique set of challenges for detection. Think of it like this: a massive galaxy cluster is a blazing bonfire of X-ray emission, its enormous gravity compressing and heating the gas within it to temperatures of tens of millions of degrees, making it shine brightly for our telescopes. A galaxy group, by comparison, is more like a collection of campfires. The gravitational pull is weaker, so the gas in the intragroup medium is not squeezed as tightly. It's still hot, typically in the range of a few 100,000 to 10 million degrees, but it's also much more diffuse. This puts it in a particularly awkward observational sweet spot, or rather a blind spot. It's often too hot to be seen in the ultraviolet light of neutral hydrogen, yet too faint and spread out to produce a strong, distinct X-ray glow like a cluster. This faintness means that for a long time, the intragroup medium was largely a theoretical concept. We knew it had to be there, but actually weighing it was extraordinarily difficult. However, advances in X-ray astronomy, particularly with the immense sensitivity of telescopes like XMM Newton and Chandra, have begun to change that. Astronomers have to conduct extremely long, patient exposures, sometimes staring at a single galaxy group for days, to collect enough X-ray photons to see the faint, wispy halo of gas that permeates the space between the member galaxies. When they succeed, the results are illuminating. They reveal that this intragroup medium is often enriched with heavy elements like oxygen, silicon, and iron, elements that can only have been forged in the hearts of stars and then blown out into the group environment by the same galactic winds we discussed earlier. The very presence of these metals tells a story of a dynamic ecosystem where material is constantly being recycled from the galaxies into their shared surroundings. Studying these groups is not just about finding another hiding place, it's about completing the cosmic Baryon budget on every scale. Cosmology gives us a global number, the total amount of baryons in the universe. But to understand how the universe works, we need to know how that matter is distributed. How much is locked in stars and cold gas within galaxies? How much is in the hot plasma of massive clusters? And critically, how much resides in these intermediate environments, the galaxy groups and their surrounding gas? By carefully measuring the properties of the intragroup medium in many different systems, astronomers can start to answer this. They can determine what fraction of a group's total mass is made up of this hot gas, and then extrapolate that to the countless other groups throughout the cosmos. This provides a crucial constraint, a vital data point that helps us understand the efficiency with which baryons are funneled into different structures over cosmic time. The investigation into galaxy groups reveals a more nuanced picture of the missing baryon problem. It suggests the missing matter isn't located in one single, monolithic reservoir, but is instead distributed across a spectrum of environments, from the vast cosmic web filaments down to these more intimate galactic associations. Each of these hiding places contributes a piece to the overall puzzle. The faint, hard-to-detect glow of the intragroup medium may not be as dramatic as the intense X-ray blaze of a cluster, but its collective contribution, given the sheer number of groups in the universe, is immense. By accounting for the baryons in these local galactic neighborhoods, we take another significant step toward closing the ledger, proving that what is missing is not gone, but simply waiting for us to develop the sensitive tools and clever methods needed to bring it out of the shadows. Zooming in even further from the grand cosmic web and the intimate scale of galaxy groups, we arrive at the very doorstep of individual galaxies themselves. This brings us to our 12th clue, a dynamic and complex region known as the circumgalactic medium, or CGM. If a galaxy were a planet, the CGM would be its atmosphere, a vast, extended halo of gas, dust, and plasma that can stretch for hundreds of thousands of light-years far beyond the galaxy's visible stars. This isn't a calm, static shroud. It's a chaotic and bustling galactic port, a place of constant activity where material is arriving, departing, and being processed. The CGM is the critical interface, the frontier where a galaxy interacts with the wider intergalactic environment, and it's becoming increasingly clear that it holds vital clues to the whereabouts of the missing baryons. To understand the CGM's role, we need to see it as a cosmic recycling center. It's fueled by two powerful opposing flows. On one hand, you have the outflows we discussed earlier, the supernova-driven winds and AGN jets that violently eject gas from the galaxy's disk, hurling it out into the halo. This is the galaxy actively expelling its own building materials. On the other hand, you have accretion, the steady, gentle rain of fresh, primordial gas constantly falling in from the intergalactic medium, drawn by the galaxy's gravity. This incoming gas is the future fuel for star formation. The CGM is where these two flows meet and mix. Some of the gas blown out in winds may eventually cool down and fall back onto the galaxy in a process called galactic recycling, like a fountain that spouts water high into the air only for it to fall back down. This cycle regulates a galaxy's life, controlling how fast it forms stars and how quickly it evolves. So, how does this connect to our search for the universe's missing normal matter? The key is in the sheer mass and state of the gas within these galactic halos. Observations have revealed that the CGM contains an astonishing amount of material, often holding as much or even more mass in gas than all the stars within the galaxy itself. This gas exists in a multiphase state, meaning it's not all at one temperature. It's a turbulent soup containing cool, dense clouds of neutral hydrogen, warmer ionized gas, and extremely hot diffuse plasma. It's this hot, extended component of the CGM that acts as a direct bridge to the warm, hot intergalactic medium. The outflows from the galaxy heat and inflate this halo, creating a massive, hot atmosphere that can seamlessly blend into the hotter filaments of the cosmic web. Some of the baryons that were once considered missing may, in fact, be residing right here, in these immense, hard-to-detect gaseous envelopes surrounding every galaxy. Detecting the CGM requires the same clever, multi-wavelength approach as finding the WHIM. Astronomers use the light of distant quasars as piercing needles to probe these galactic halos. By looking at a quasar's spectrum whose line of sight skims past a foreground galaxy, they can identify a series of absorption lines. These lines reveal the composition, temperature, and density of the gas in that galaxy's CGM at a very specific location. Cool gas shows up as absorption from neutral hydrogen in the ultraviolet, creating a Lyman alpha forest on a local scale. Warmer gas reveals itself through ions like magnesium and silicon. And the hottest plasma, the part most closely connected to the missing baryon problem, is detected through highly ionized oxygen, the same OVI and O-7 signatures we hunt for in the wider web. These observations confirm that galaxies are not isolated islands. They are surrounded by massive, complex ecosystems of gas. The significance of the circumgalactic medium lies in its role as a baryon accounting unit. When we count the mass in a galaxy's stars and its immediate cold gas, we come up short. But when we add in the immense reservoir of its hot CGM, the budget for that galaxy starts to look much more balanced. The baryons aren't truly lost. They haven't traveled to some distant, unknown void. They are often still associated with their home galaxy, but in a hot, extended form that our traditional surveys simply couldn't see. This realization reframes the entire missing baryon problem. It suggests that a substantial portion of the missing matter is not floating freely in the deepest voids, but is instead bound up in the colossal atmospheres of galaxies, a vast and hidden component of galactic mass that we are only now beginning to appreciate and measure, bringing us one step closer to a full accounting of the ordinary matter in the cosmos. Just when we thought we had exhausted the universe's bag of tricks for revealing its hidden matter, nature unveiled one of the most enigmatic and powerful tools yet: fast radio bursts. Imagine a flash of radio light so brilliant it can outshine an entire galaxy, but one that lasts for less time than the blink of an eye. These are FRB's mysterious millisecond duration pulses of radio waves that travel to us from galaxies billions of light years away. For years, their origin was one of astrophysics' greatest puzzles, with theories ranging from colliding neutron stars to highly magnetized stellar corpses. But as we've begun to understand them, a remarkable realization has dawned. Their incredible power and vast distance make them nearly perfect cosmic probes, and they are now revolutionizing our ability to finally weigh the missing baryons in a way we never could before. The secret lies in a property known as dispersion. As a fast radio burst travels across the vast, not-so-empty intergalactic medium, its journey is not a simple, unimpeded sprint. The radio waves are passing through a sea of free electrons, the very same ionized particles that make up the warm, hot intergalactic medium. Now, here's the crucial part. These electrons don't affect all radio frequencies equally. Lower frequency radio waves interact with the electrons more strongly than higher frequency waves. This interaction slows them down, just like light bends when it enters water. The result is that the different colors of the radio burst, from the lowest pitches to the highest, begin to separate during their epic journey. The higher frequencies race ahead while the lower frequencies lag further and further behind. By the time the entire burst arrives at our radio telescopes here on Earth, what was once a sharp, simultaneous spike has been stretched out into a distinctive descending chirp. We hear the high notes first, followed by a sweeping slide down to the lowest notes. This delay, this spreading out of the signal, is the dispersion measure. And it is a direct and exquisitely sensitive gauge of the total number of electrons the burst encountered along its path. It's like having a cosmic ruler for charged particles. The longer the delay between the arrival of the high and low frequencies, the more electrons the signal has traveled through, since these free electrons are inextricably tied to protons in the ionized plasma of the WHIM. Measuring the electron density directly gives us a count of the baryons. For the first time, we have a method that doesn't rely on subtle shadows, faint glows, or complex statistical stacking. A single, pristine fast radio burst provides a clean, integrated measurement of the total baryonic matter in a giant cylinder of space stretching all the way from the burst's host galaxy to our own. This makes FRBs arguably the most powerful tool yet deployed in this cosmic investigation. Unlike quasars, whose light comes from a complex and messy environment around a black hole, a fast radio burst is a much simpler, cleaner signal. It's a brief, brilliant flash whose dispersion is almost entirely due to the material between galaxies, giving us a less contaminated reading of the WHIM itself. Furthermore, because they are so incredibly bright, we can detect them from much further away than we can see individual quasars in detail, allowing us to probe the cosmic web across vast cosmic distances and trace how its baryon content has evolved over time. Each new burst detected is like taking a core sample from the universe, drilling through billions of light years of cosmic structure and extracting a direct measurement of its hidden material. As our telescopes discover more and more of these fleeting events, they are weaving together a web of measurements that is finally, directly, and unequivocally accounting for the long-lost ordinary matter that has been woven into the fabric of the cosmos all along. While fast radio bursts provide a modern and direct probe, one of the most profound clues in our investigation is actually a fossil, an echo from the universe's very first moment of sound. To understand this, we have to travel back to a time before the first stars, before the first atoms, to a universe so dense and hot that it was an opaque, seething plasma. In this primordial fireball, ordinary matter, protons and electrons, was coupled with light in a relentless tug of war. Gravity would try to pull the matter together into denser clumps, while the intense radiation pressure of the trapped photons would push it back out, creating powerful, rhythmic waves that propagated through the infant cosmos. These were literal sound waves, traveling at a significant fraction of the speed of light, compressing and rarefying the plasma in a cosmic symphony. This concert, however, had a very abrupt finale. About 380,000 years after the Big Bang, the universe had expanded and cooled just enough for electrons and protons to combine into neutral hydrogen atoms. In an event known as recombination, the universe suddenly became transparent. The photons, which had been constantly scattering off the free electrons, were suddenly set free, streaming across space to eventually become the cosmic microwave background we observe today. This instant of decoupling had a dramatic effect on those sound waves. With the photons no longer providing the outward pressure, the waves effectively froze in place. The compressions and rarefactions in the plasma were instantly locked into the distribution of matter, like a phonograph record pressed at the moment of recombination. The distance these sound waves could travel from the Big Bang until that moment became a fixed, standard scale imprinted on the cosmos. This frozen scale is what we call the Baryon acoustic oscillation, or BAO. It manifests as a subtle, statistical preference for galaxies to be separated by a specific distance. When we create immense three-dimensional maps of the universe, plotting the positions of millions of galaxies, we don't see a perfectly random scatter. If you were to pick any galaxy and measure the distances to all its neighbors, you would find a small but significant excess of galaxies situated at a very particular separation from one another. That preferred separation is the radius of that primordial sound wave shell, a standard ruler etched into the very fabric of cosmic structure. Today, that ruler measures about 500 million light-years across, a colossal imprint of the universe's earliest vibrations. So, how does this ancient ruler help us find the missing baryons of today? The key is that the BAO provides an exquisitely precise measurement of the geometry and expansion history of the universe. Because we know the true physical size of this standard ruler from our understanding of the early universe, we can measure its apparent size in the sky at different cosmic epochs. By observing the BAO signature in galaxy maps from, say, 5 billion years ago and comparing it to maps from 10 billion years ago, we can see how much the universe has stretched in that time. This gives us a direct and powerful way to measure the rate of cosmic expansion and the influence of dark energy. But more than that, the strength and clarity of the BAO signal depend critically on the initial conditions set by the Baryons. The very existence of those sound waves relied on the interplay between radiation pressure and the gravitational pull of the ordinary matter. The amount of baryons present in the early universe determined how pronounced these oscillations would be. When astronomers analyze the cosmic microwave background, they see the BAO pattern imprinted there as well in the hot and cold spots of the ancient light. Combining this early universe snapshot with the BAO measured in much later galaxy maps creates an incredibly powerful constraint. It tells us with great certainty the total budget of baryons that must have existed from the beginning and how they were distributed as the large-scale structure formed. If the amount of baryons we see in galaxies and the hot gas of clusters falls short of this BAO inferred total, then the remainder must be elsewhere precisely in the diffuse WHIM that permeates the cosmic web. The BAO doesn't directly detect the missing matter, but it acts as the ultimate cosmic accountant, providing the final, non-negotiable number that our local inventories must eventually add up to. It confirms that the missing baryons aren't a myth, they are a mathematical certainty, and their hiding place is the vast, interconnected network of the cosmic web, a structure whose very form was dictated by these same sound waves that first rang out at the dawn of time. But to truly map this cosmic web, we need to see it not just in isolated threads, but as a complete, glowing tapestry. This brings us to our 15th clue, a subtle but all-encompassing phenomenon known as the soft X-ray background. If you could somehow see the sky with X-ray eyes, you wouldn't just see the brilliant pinpricks of distant black holes and exploding stars. You would also perceive a faint, pervasive glow, a uniform light that seems to come from everywhere at once. This is the diffuse X-ray background, and for decades it was considered a perplexing fog, a kind of unresolved noise in the high-energy sky. But within that fog, astronomers suspected, might be the collective, incredibly faint emission from the very filaments of the warm, hot intergalactic medium we've been hunting. The challenge, however, is one of cosmic forensics. This background glow isn't a pure signal from the WHIM. It's a complicated cocktail of light from many different sources, all layered on top of each other. It's like trying to hear a single, quiet instrument in a symphony playing from a distant room. The first and most local component is our own cosmic backyard, a region known as the local hot bubble. This is a cavity in the interstellar medium surrounding our solar system, filled with a thin, million-degree plasma. While its exact origin is still debated, perhaps the remnant of an ancient supernova explosion, it contributes a significant portion of the very low energy, or soft, X-rays we see across the entire sky. Then there's the contribution from far more distant but extremely powerful sources. The integrated light from all the active galactic nuclei and quasars across the universe, whose fierce X-ray beams crisscross space, adds up to create a substantial part of the higher energy background. So how do we find the whisper of the WHIM in this cosmic cacophony? The answer lies in a meticulous process of modeling and subtraction. Astronomers act like master chefs trying to identify a single, subtle spice in a complex dish. First, they build incredibly detailed models of all the known ingredients. They use data from all sky surveys to map the precise intensity and energy signature of the local hot bubble's emission. They then use deep field observations from telescopes like Chandra and XMM Newton to resolve and count as many individual distant AGN as possible, calculating their total combined contribution to the X-ray haze. Once these major components are carefully quantified, they are digitally subtracted from the total observed background. What remains after this painstaking cleaning process is a residual signal, a leftover glow that cannot be explained by the local bubble or the known population of distant point sources. This residual is the holy grail in this particular line of investigation. According to theoretical models, the vast, tangled filaments of the WHIM, while incredibly faint individually, should collectively produce a very specific, diffuse signature in this soft X-ray band. The highly ionized oxygen and other elements in the hot plasma can emit X-ray photons as free electrons recombine with ions or as they collide and excite one another. While the surface brightness of any single filament is minuscule, the sheer cumulative area covered by the cosmic web across the entire sky means its total emission could add up to a detectable, all-pervasive whisper. Isolating this signal is one of the most demanding tasks in modern X-ray astronomy. It requires not just sensitive instruments, but a profound understanding of every possible contaminant, from the solar wind's interaction with Earth's magnetosphere to the faint X-ray emission from even our own galaxy's hot corona. The latest results from missions like the Spectre RG Observatory, with its advanced all-sky survey capabilities, are now providing the high-precision, low-noise maps needed for this delicate work. Early analyses are tantalizing. In certain energy bands and after subtracting the best models of known components, there does appear to be an excess, a faint, smooth glow that aligns with predictions for the large-scale structure. It's not a direct image of the cosmic web. That would require a telescope of unimaginable size, but it is a statistical detection of its presence. This diffuse residual provides yet another independent line of evidence, a testament to the fact that the space between galaxies is not a true void, but is in fact filled with a seething, hot ocean of ordinary matter, its faint collective breath finally registering on our most sensitive detectors. As we've traced the path of the missing baryons through X-rays and radio waves, there's another critical part of the light spectrum that holds immense promise, a region where the universe whispers secrets it shouts nowhere else. This brings us to our 16th clue, a frontier of observation that pushes the very limits of our technology, the ultraviolet and extreme ultraviolet bands. Imagine the electromagnetic spectrum as a vast keyboard. We've become adept at hearing the deep bass of radio waves and the high treble of X-rays, but there's a crucial set of middle notes, the UV and UV range, that has been notoriously difficult to tune into, especially for objects outside our own galaxy. The reason is as simple as it is frustrating. Our atmosphere acts as a perfect shield, blocking almost all ultraviolet light from reaching the ground. And the interstellar medium, the thin gas and dust between the stars, is incredibly effective at absorbing the most extreme ultraviolet photons. This creates a double barrier, making the UV band one of the final, great uncharted territories in observational astronomy. Yet, it's precisely in this challenging domain that we expect to find some of the most telling signatures of the warm-hot intergalactic medium. The key lies in the ionization states of the elements within the gas. While the hottest parts of the WHIM, with their fully stripped oxygen nuclei, reveal themselves in X-rays, there is a vast, cooler component. Think of it as a lukewarm phase with temperatures ranging from 10,000 to a few 100,000 degrees. In this temperature range, heavy elements like oxygen, nitrogen, and carbon are only partially ionized. They still hold onto some of their electrons, and these electrons can jump between specific energy levels, emitting or absorbing light at very precise wavelengths. For many of these crucial ions, their strongest, most prominent transitions happen to fall right in the ultraviolet and extreme ultraviolet parts of the spectrum. It's as if each type of ion has its own unique ringing frequency, and for the cooler baryons in the cosmic web, that frequency is a UV chime. Detecting this chime, however, requires us to get above Earth's protective blanket and peer through the fog of our own galaxy. Past missions like the Hubble Space Telescope have done heroic work in the far and near ultraviolet, using the light of quasars to find absorption lines from these cooler ions in the circumgalactic medium of relatively nearby galaxies. But to probe the true intergalactic wilderness, the filaments of the WHIM that stretch between superclusters, we need to go further into the more energetically extreme ultraviolet. This is the domain where future telescopes, specifically designed with novel technology to handle the difficulties of UV astronomy, could change everything. Instead of relying solely on the difficult task of spotting faint absorption lines against the brilliant but rare backdrop of quasars, these next-generation observatories might be able to do something even more revolutionary: see the WHIM glow. The concept is as straightforward as it is powerful. The same ions that absorb UV light can also emit it. As free electrons collide with ions like OVI or Ni Roman 8 in the WHIM, they can excite them, causing them to release a photon at their characteristic UV wavelength. While the emission from any single cubic light-year of space would be vanishingly faint, the cumulative effect of a massive filament stretching for millions of light-years could theoretically be detected as an extremely diffuse, gentle glow. Mapping this faint emission would be the ultimate prize. It would allow us to transition from inferring the web's structure through statistical shadows and stacked data to potentially seeing its outline directly, tracing the intricate architecture of the cosmic web in the same way that long-exposure photography can reveal the faint, beautiful structure of a nebula. This would provide a completely independent and complementary method to X-ray absorption studies, one that is sensitive to a different, crucial temperature regime of the missing matter. The path to achieving this vision is laden with technical hurdles. UV photons are easily scattered and absorbed, requiring telescopes with supremely smooth and efficient mirrors. The detectors must be exquisitely sensitive to count the trickle of expected photons, and the entire instrument must contend with the bright, local UV background from our solar system. Yet, the scientific payoff is so profound that concepts for such missions are actively being developed. By opening this new window onto the universe, we would not just be finding the missing baryons, we would be painting a full-color picture of them, distinguishing the hot X-ray threads from the warm UV strands, and finally understanding the complete thermal tapestry of the cosmic web. This elusive glow, waiting to be captured, represents the potential to move from a successful detective story to a grand cartographic mission, mapping the hidden continents of the ordinary universe in a light we have only just begun to see. To truly understand how the universe managed to hide half of its ordinary matter, we have to rewind the cosmic clock to a period of profound transformation, a time when the very nature of space itself was being fundamentally rewritten. This brings us to a pivotal chapter in cosmic history known as the Epoch of Reionization, a dramatic event that likely played a crucial role in cooking the intergalactic medium into the hot, invisible state we struggle to observe today. For the first few 100,000 years after the Big Bang, the universe was a relatively simple and dark place. It was filled with a fog of neutral hydrogen and helium gas, a silent, opaque expanse where light could not travel freely. But this calm was not destined to last. Deep within the gravitational wells of the first dark matter structures, the very first stars began to flicker on. These were not the gentle, steady stars like our sun. They were behemoths, monsters 100 times more massive, blazing with a ferocious intensity and living short, explosive lives. The light from these first stars and the earliest quasars was unlike anything the universe had seen before. It was a torrent of extremely energetic ultraviolet photons that began to flood the cosmos. When these high-energy photons encountered an atom of neutral hydrogen, they delivered a powerful kick, blasting the electron clean off the nucleus. This process, called ionization, began to rip the universe apart atom by atom, transforming it from a neutral fog into a transparent, ionized plasma. Think of it as a great cosmic thaw, where islands of clarity began to appear around the first luminous objects, eventually expanding and merging until the entire universe was reionized, a process that was largely complete by the time the universe was about 1 billion years old. This epoch didn't just clear the fog, it fundamentally changed the thermal state of the vast reservoirs of gas that had not yet collapsed into galaxies. All that energy pouring out from the first stars and quasars didn't just ionize the gas, it heated it, pumping tremendous thermal energy into the intergalactic environment. This is the critical connection to our missing baryons. The reionization process was not a gentle warming, it was a violent, universal heating event. The energy required to rip electrons from atoms across the entire cosmos was staggering, and that energy had to go somewhere. A significant portion of it was converted into heat, raising the temperature of the intergalactic gas from a frigid few tens of degrees above absolute zero to tens of thousands, even hundreds of thousands of degrees. This heating effectively set the initial conditions for the modern warm-hot intergalactic medium. It preheated the entire cosmic web, raising the baseline temperature of the baryons that would later flow into the filaments and sheets of large-scale structure. This preheating meant that when gravity later began to pull this gas into the cosmic web, it was already puffed up and resistant to collapsing into the cool, dense clouds that form stars and are easy for our telescopes to see. The reionization epoch essentially primed the pump, ensuring that a vast portion of the universe's ordinary matter would remain in a hot, diffuse state, making it inherently more difficult to detect and setting the stage for the great disappearance act we are trying to solve. The legacy of reionization is therefore written in the very temperature and ionization state of the hidden baryons we are hunting today. When we detect absorption lines from highly ionized oxygen in the WHIM, we are seeing the descendants of that primordial heating event. The violent births and deaths of the first generations of stars didn't just light up the cosmos, they also orchestrated the greatest hiding place in history by transferring enough energy into the intergalactic medium to keep it hot and elusive for billions of years. This deep connection ties one of the most important milestones in cosmic evolution directly to our modern-day puzzle, showing that the missing baryon problem isn't a recent anomaly, but a natural consequence of the universe's fiery and dramatic adolescence. Armed with all these incredible observational clues, from the ghostly shadows in quasar light to the faint echoes of fast radio bursts, you might wonder how we can possibly piece them all together into a single, coherent picture of the cosmic web. The answer lies not just in our telescopes, but in our ability to create entire universes inside machines. This brings us to the powerful, predictive engine that guides our entire investigation, the supercomputer simulation. These are not simple video game recreations. They are some of the most complex and computationally intensive calculations ever performed by humanity. Virtual laboratories where we can test our theories of cosmic evolution from the Big Bang to the present day, providing our 18th crucial clue in the hunt for the missing baryons. To build a virtual universe, scientists start with the fundamental laws of physics as we understand them. The equations governing gravity, the dynamics of gases, the processes of heating and cooling, and the formation of stars and black holes. They then set the initial conditions to match what we observe in the cosmic microwave background, that pristine baby picture of the universe. Into this expanding digital box, they sprinkle the ingredients we know must be there. A vast sea of dark matter to provide the gravitational backbone, and a smaller but critical amount of ordinary baryonic matter. With a push of a button, the simulation begins, running for millions of CPU hours to fast-forward the evolution of the cosmos over 13.8 billion years. The supercomputer calculates the gravitational tug between trillions of dark matter particles, while simultaneously modeling how the normal matter flows, collides, and heats up in response. What emerges from these digital cauldrons is nothing short of breathtaking. As the simulation progresses, the initially smooth distribution of matter begins to clump and cluster, exactly as predicted by theory. A sprawling, intricate cosmic web materializes on the screen, complete with vast, empty voids, long, delicate filaments, and dense, massive clusters of galaxies at the intersections. And within this digital tapestry, the simulation makes a very specific and critical prediction about the fate of the Baryons. It shows that as structure forms, shock waves ripple through the intergalactic medium, heating vast amounts of gas to temperatures of millions of degrees. The simulations consistently show that a huge fraction of the universe's normal matter, right around that elusive 50%, does not end up in shiny stars or cold galactic disks. Instead, it is driven by gravitational forces and energetic feedback into these vast, diffuse reservoirs of hot, ionized gas that precisely match our definition of the warm-hot intergalactic medium. The WHIM is not just a convenient theory, it is the inevitable outcome of how cosmic structure forms. These virtual universes do more than just confirm the WHIM existence, they give us a detailed map of its expected properties. They predict the range of temperatures and densities we should find in different parts of the cosmic web, from the hotter, denser gas near massive clusters to the cooler, more tenuous strands in the wider voids. They tell us how much highly ionized oxygen we should expect to see and what the statistical patterns in the Lyman alpha forest should look like if the WHIM is indeed present. This predictive power is what makes simulations such an indispensable guide. They act as a cosmic Rosetta Stone, translating the indirect, often confusing signals we receive from our telescopes into a concrete understanding of the underlying physical processes. When we observe a specific pattern of absorption lines in a quasar spectrum, we can run a simulation and ask, what distribution of gas in the cosmic web would create a pattern exactly like this? The simulation provides the answer, allowing us to reverse engineer the observed data to understand the true structure of the hidden universe. The relationship between simulation and observation is a continuous, dynamic dialogue, a process of refinement that sharpens our search. Sometimes the observations come first, presenting us with a puzzling new phenomenon. Astronomers then rush to their simulations, tweaking the physics and initial conditions to see if they can reproduce what the telescopes have found. At other times, the simulations lead the way, predicting a faint signal or a specific structure that should be out there. This sends observers back to their instruments with a clear target, a specific wavelength to scan, or a particular region of sky to stare at with unprecedented sensitivity. For instance, early simulations predicted the specific absorption signatures of O-7 and O-8 long before our X-ray telescopes were sensitive enough to detect them, giving astronomers a precise shopping list of what to look for. When those predicted lines were finally, tentatively observed, it was a triumphant validation of the entire simulation-led approach. This iterative process is how we close in on the truth. If a simulation predicts a strong Sunyaev-Zeldovich signal from a filament that our telescopes cannot detect, it forces us to ask critical questions. Is our simulation missing a key piece of physics, like a more accurate model of how galactic winds inject energy? Or are our observational techniques simply not sensitive enough yet, requiring longer exposures or new technology? This back and forth has been essential for understanding the role of galactic feedback. Early simulations that did not include the potent effects of supernova winds and active galactic nuclei found that too many baryons cooled down and formed stars, leaving the WHIM depleted. It was only by adding these violent, energetic processes that the simulations began to match the real universe, showing how winds can efficiently pump gas out of galaxies and heat it to the temperatures required to hide it in the web. The simulations, therefore, don't just predict where the missing baryons are. they explain the very mechanisms that put them there, painting a dynamic and sometimes violent picture of a cosmos where galaxies and the intergalactic medium are in a constant, energetic dance. They provide the crucial theoretical framework that turns a collection of individual clues into a single, compelling story of cosmic evolution, guiding our every step as we continue to weigh the hidden half of the universe. So far, our investigation has taken us across the vast, empty-seeming stretches of the cosmic web. But there is another place we can look to tighten the case, a place where the universe's accounting books are surprisingly balanced. This is our 19th clue, and it lies in the heart of the largest gravitationally bound structures in existence, rich galaxy clusters. These colossal metropolises, teeming with thousands of galaxies, are more than just spectacular sights. They are pristine cosmic laboratories. Because they are so massive, they have a powerful gravitational pull strong enough to hold onto virtually all the material that was originally within their vast domain, including both dark matter and the ordinary baryonic matter. This makes them a perfect place to conduct a detailed local census, to check if the cosmic ledger balances on this smaller but still immense scale. When astronomers perform this inventory within a galaxy cluster, they measure three primary components. First, they tally the mass locked in stars, which is all the visible light from the billions of stars within all the cluster's member galaxies. Second, and far more significantly, they measure the hot intracluster medium. This is the incredibly hot, thin plasma that fills the space between the galaxies, a gas heated to temperatures of tens of millions of degrees that it shines brightly in X-rays. This gas is the dominant reservoir of normal matter in the cluster, often containing several times more mass than all the stars combined. Finally, using the motion of the galaxies themselves and the subtle distortions of background light caused by gravitational lensing, they can measure the cluster's total mass, which is overwhelmingly dominated by dark matter. The crucial step is then to take the sum of the baryonic mass, the stars plus the hot gas, and divide it by the total mass. This gives the cluster's baryon fraction. What they find is both revealing and consistent. Across countless galaxy clusters, this measured baryon fraction comes out to roughly 15%, give or take a small amount. And this number aligns almost perfectly with the universal baryon fraction we derived from the cosmic microwave background and Big Bang nucleosynthesis. This is a profound result. It means that within these massive, closed systems, the universe's original recipe of dark matter to normal matter has been preserved. Galaxy clusters have held onto their fair share of the cosmic bounty. They are not missing their baryons. In fact, they have the exact amount they were supposed to get from the initial conditions of the cosmos. This successful accounting within clusters acts as a critical control for our entire investigation. It tells us that our fundamental understanding of the baryon budget is correct. The laws of physics and our methods of measurement are sound. The problem, therefore, cannot be that baryons have been mysteriously destroyed or that our core cosmological model is wrong. This success inside clusters, however, makes the failure of the wider census even more striking. It creates a powerful "where else" argument. If these giant structures, which represent the densest peaks of the cosmic web, have their full complement of baryons, then the missing half must be residing in the less dense, more widespread environments. The shortfall isn't happening in the brilliant, easy-to-see cities of the universe. It's occurring in the sprawling, dimly lit suburbs and the vast, open countryside of the cosmic web. The clusters themselves point an accusatory finger outward toward the very filaments that connect them. The balanced books within these massive systems force us to conclude that the lost material is not truly lost at all, but is simply sequestered in a form and location that is extraordinarily difficult to observe directly. The diffuse, hot gas of the warm, hot intergalactic medium that forms the scaffolding between these glittering galactic metropolises. But to grasp the full power of these galactic engines, we need to turn our attention to our 20th clue, a force of such immense power it can dictate the fate of entire galaxies and sculpt the cosmic web itself, the impact of active galactic nuclei feedback. At the very heart of most large galaxies, including our own Milky Way, lies a supermassive black hole, a gravitational monster weighing millions or even billions of times the mass of our Sun. While these black holes spend most of their time in a quiet, dormant state, when they actively feed on surrounding gas and dust, they transform into the most efficient energy converters in the universe. As matter spirals inward at near light speed, it doesn't just vanish. It forms a searingly hot, magnetized accretion disk that can launch twin jets of plasma and generate winds blowing outward at phenomenal speeds. This isn't a gentle breeze, it's a celestial hurricane, a colossal outburst of energy that we call AGN feedback. The sheer scale of this energy is almost impossible to overstate. A single, powerful outburst from an active galactic nucleus can release more energy than all the stars in its host galaxy combined, and this energy is delivered in a concentrated, directed fashion. These AGN-driven winds don't just push aside a little bit of gas, they can blow huge cavities in the hot gas surrounding the galaxy, creating vast bubbles that rise and expand for hundreds of thousands of light years. In some of the most massive galaxy clusters, we can actually see these colossal cavities with X-ray telescopes, appearing as dark voids in the bright, X-ray-emitting intracluster medium, silent testimony to a titanic explosion that occurred millions of years ago. This process acts as a cosmic pressure release valve. As the central black hole feasts, it generates so much power that it violently shuts down its own fuel supply, blowing the surrounding gas reservoir clear out of the galactic center. This self-regulating mechanism prevents the galaxy from forming too many stars too quickly and from growing to an unmanageable size, solving a long-standing puzzle in galactic evolution. And this is where AGN feedback becomes a master of cosmic redistribution, a prime suspect in the case of the missing Baryons. The material expelled by these winds isn't just moved from the galaxy's center to its outer edges. It is often given so much energy that it completely escapes the galaxy's gravitational pull altogether. Think of a galaxy as a deep gravitational well, a valley where baryonic matter naturally collects. AGN feedback acts like a powerful pump, actively lifting this material up and out of the valley, hurling it high into the circumgalactic medium and beyond into the true intergalactic wilderness. This process effectively takes baryons from a state where they are relatively easy to observe cold, dense, and concentrated within a galaxy, and transforms them into the exact state we've been struggling to find, hot, diffuse, and spread across millions of light years of space. The very same violent outbursts that regulate star formation are also directly responsible for cooking and dispersing a significant fraction of the universe's normal matter, seeding the cosmic web with the hot plasma that makes up the warm, hot intergalactic medium. The evidence for this profound connection is etched across the sky in the chemical makeup of the intergalactic medium itself. The powerful winds from active galactic nuclei are not composed of pure hydrogen and helium. They carry with them a rich mixture of heavy elements like oxygen, carbon, and iron elements that were forged in the hearts of stars and then churned out by supernova. When astronomers detect those telltale absorption lines from highly ionized oxygen in the distant cosmic web, they are likely seeing the scattered remains of ancient AGN outbursts, the chemical pollution from eons of black hole activity that has been mixed and spread throughout the large-scale structure of the universe. This provides a direct link between the most energetic events in galactic centers and the hidden reservoir of missing matter. The AGN didn't just hide the Baryons, it left its fingerprints all over them, enriching the WHIM with the heavy elements that now serve as our primary tracers for finding it. In this light, the missing Baryons are not a passive component of the cosmos. They are the dynamic legacy of the most powerful engines in the universe, a testament to the ongoing, violent interplay between galaxies and the supermassive black holes that lurk within them. Even as we celebrate the incredible progress in finding the missing baryons through the chemical fingerprints of oxygen, a shadow of uncertainty hangs over these measurements, forcing astronomers to confront a tricky question. Are we reading the cosmic ledger correctly, or are we misinterpreting the fine print? This brings us to a crucial and humbling 21st clue, one that deals not with the presence of the gas but with our ability to accurately weigh it. The challenge lies in the complex physics of the warm-hot intergalactic medium and the assumptions we have to make to translate a faint absorption line into a definitive number for the total mass. At the heart of this problem are two intertwined concepts, metallicity and the ionization balance. Metallicity is simply the astronomer's term for the abundance of elements heavier than hydrogen and helium, what we commonly call metals. In the context of the cosmic web, this primarily means oxygen, carbon, and nitrogen. We rely on the absorption lines from these metals, especially highly ionized oxygen, to prove the WHIM exists. But to then calculate how much total gas is there, we have to make a critical assumption about how much oxygen is mixed in with the hydrogen. Think of it like this. You're trying to measure the total amount of water in a vast, foggy lake by analyzing the concentration of a specific dye that has been mixed into it. If you know the exact ratio of dye to water, then measuring the dye's strength tells you everything about the lake's total volume. But if you're uncertain about that initial dye-to-water ratio, your final estimate for the lake's size could be wildly off. This is precisely the dilemma we face with the WHIM. When we detect an absorption line from O-7, we are measuring the amount of that specific ion along our line of sight. To convert that number into a total column density of all baryons, the vast sea of hydrogen and helium protons and nuclei that the oxygen is floating in, we must assume a metallicity. We have to guess how enriched this intergalactic gas is. If we assume the metallicity is high, it means there's a lot of oxygen relative to hydrogen, so the strong absorption line we see implies a smaller total reservoir of gas. If we assume the metallicity is low, the same strong line would imply a truly colossal amount of hydrogen and helium, because it would take a much larger volume of gas to produce the same amount of absorbing oxygen. The problem is, we don't have a surefire way to know the true metallicity of these remote filaments. Unlike in galaxy clusters where the gas is dense and we can measure multiple elements to get a good average, the WHIM is too diffuse. We often only detect one or two types of ions, making a precise metallicity measurement nearly impossible. Astronomers typically make an educated guess based on models of galactic winds and simulations of cosmic chemical evolution. They might assume the WHIM has a metallicity around 1/10 or 1/3 of the Sun's value, but this is a huge range of uncertainty. Depending on which value you choose, your final estimate for the baryon content of that filament can change by a factor of 3 or more. This isn't a small error bar, it's a fundamental ambiguity that affects our entire census, making it difficult to say with absolute certainty whether we've accounted for the full 50% or if we're still a little short. Compounding this metallicity problem is the equally tricky issue of ionization balance. An atom like oxygen can be stripped of its electrons to different levels. OVI has lost 5 electrons, O-7 has lost 7, and O-8 has lost all 8. The fraction of oxygen atoms in any one of these states depends almost entirely on the temperature and density of the surrounding gas. It's a delicate dance between collisions that knock electrons off and recombinations that stick them back on. To go from the amount of O-7 we observe to the total amount of all oxygen in the filament, we need a precise model of this ionization balance. We have to calculate what fraction of the total oxygen pool is in the O-7 state at the presumed temperature of the WHIM. If our temperature estimate is wrong by even a factor of 2, that fraction can change dramatically, throwing off our mass calculation. the situation is even more complex because the WHIM is not a uniform oven. It contains a mix of temperatures and densities. A single absorption line might be produced by a blend of gas at slightly different conditions, making it incredibly difficult to pin down the one true ionization correction needed to get the right answer. This layered uncertainty, first in the metallicity and then in the ionization fraction, means that every beautiful, clear absorption line we detect carries with it a hidden world of assumptions and potential errors, reminding us that the final chapter in the story of the missing Baryons is still being written, with every number subject to revision as our understanding of these subtle atomic processes deepens. This brings us to a truly ingenious strategy, our 22nd clue, one that allows astronomers to see the cosmic web not by finding it directly, but by listening to the synchronized hum of the universe itself, the cross-correlation technique. Imagine you're at a vast, crowded party, a cacophony of thousands of simultaneous conversations. You're trying to listen in on one specific person, but their voice is far too quiet to pick out from the general roar. Now imagine you have a friend who knows that person's exact location in the room. If they could point right at them, and if you could focus your hearing on just that one spot, you might have a chance. Cross-correlation is the scientific version of this. Instead of relying on a single, clear signal that may be too faint to hear, we combine two or more different, noisy datasets. We use one map of the cosmos that tells us where to look, and another map that contains the faint whisper of the signal we're trying to detect, and by overlaying them perfectly, we can extract a conversation that was previously lost in the cosmic static. The process works by hunting for a statistical relationship. Astronomers take two completely different views of the same patch of sky. The first map is typically a precise three-dimensional chart of galaxy positions from a massive survey. Galaxies are the bright signposts of the cosmic web. They trace out the underlying gravitational skeleton of dark matter, marking the dense knots and the long, filamentary structures where we expect the WHIM to reside. This galaxy map tells us the address of the cosmic web. The second map is something much more subtle. It could be a map of the cosmic microwave background, specifically processed to highlight the tiny distortions from the Sunyaev-Zeldovich effect. Or it could be a map of the diffuse X-ray background, or even the dispersion measures from many fast radio bursts. This second map contains the incredibly faint signal we believe is produced by the warm hot gas, but it's buried under a mountain of unrelated noise and foreground contamination. Here's where the statistical magic happens. A computer program then scans these two maps together, pixel by pixel, or more accurately, volume by volume in space. It asks a simple but powerful question. Is there a consistent, above-average signal in map B precisely in the locations where map A tells us the cosmic web is? If the WHIM is truly concentrated in the filaments and clusters traced by the galaxies, then when we look at the CMB data at those specific coordinates, we should see, on average, a slightly stronger SZ distortion than in random, empty parts of the sky. The key word is on average. In any single filament, the signal might be too weak to claim a detection. But by analyzing thousands of filaments and clusters and calculating the average CMB distortion associated with them, a clear pattern emerges. The random noise in the CMB map averages out to zero, but the coherent, albeit faint, signal from the hot gas in all those web-like structures adds up, creating a statistically significant detection that is undeniable. This technique has been brilliantly applied to data from the Planck satellite, which created an all-sky map of the cosmic microwave background, and large galaxy surveys like the Sloan Digital Sky Survey. Astronomers took the Planck SZ map, which is a messy tapestry of primordial CMB fluctuations, instrumental noise, and the faint imprints of hot gas, and they cross-correlated it with the positions of over 1 million galaxies. The result was a resounding confirmation. They found a clear, positive correlation. The regions of space densely populated with galaxies showed a stronger SZ effect than the emptier voids. But the real breakthrough was that this SZ signal extended far beyond the known boundaries of the galaxies and even the hot gas in their immediate clusters. This extended halo of electron pressure was a direct measurement of the warm-hot intergalactic medium in the enveloping cosmic filaments. It was the ghostly outline of the web itself, revealed not by seeing it in one place, but by proving its pervasive presence through the collective power of statistics. It's as if the universe's hidden structure finally agreed to pose for a photograph, but only by combining a million different blurry snapshots into one perfectly clear composite image. Yet another layer of complexity in this cosmic mystery involves forces that are completely invisible yet may shape the very structure of the hidden matter we're seeking. This is our 23rd clue, and it pulls us into the elusive realm of intergalactic magnetic fields. We often think of the voids between galaxies as true emptiness, but they are threaded with unimaginably large yet incredibly weak magnetic fields. These fields are not the strong, focused magnets you're familiar with. They are more like a faint cosmic cobweb of energy stretching for millions of light years. The origins of these vast magnetic fields are still debated. They could be primordial, seeded in the universe's very first moments, or they could have been blown out from galaxies by the same powerful winds that distributed the Baryons themselves. Regardless of their source, their potential influence on the warm-hot intergalactic medium is profound, affecting both its structure and our ability to find it. The primary way magnetic fields influence the WHIM is by altering how heat moves through it. In a perfectly uniform, non-magnetic gas, heat is carried by the random motion of particles, a process known as conduction. This tends to smooth out temperature differences, like stirring a hot cup of coffee until it's evenly warm. But when you lace this gas with a magnetic field, everything changes. The charged particles, the electrons and ions that make up the WHIM, become tied to the magnetic field lines. They can move freely along the direction of the field, but their motion across it is severely restricted. This means that heat conduction becomes highly anisotropic. It operates efficiently along the magnetic field lines, but is strongly suppressed across them. Imagine a room where warmth can only travel along specific, invisible wires crisscrossing the space, while the air between the wires remains stubbornly cold. This is the kind of environment magnetic fields create in the cosmic web. This suppression of heat flow has a dramatic consequence. It can prevent the WHIM from mixing smoothly. Without magnetic fields, the hottest gas from galactic winds might be expected to dissipate its energy and blend evenly with the cooler surrounding medium. But with magnetic fields present, distinct pockets of hot and cooler gas can persist side by side for much longer. This can lead to a phenomenon known as thermal instability, where the gas fragments into a multiphase medium, a complex mixture of hot, diffuse plasma and cooler, denser clumps or cloudlets, all coexisting within the same filament. Theorists using sophisticated computer models have shown that this magnetic fraying of the cosmic web could be crucial. It suggests the WHIM is not a simple, uniform fog, but a far more intricate and clumpy substance, with tiny, dense knots of cooler gas suspended like dew droplets within a vast, hot atmospheric haze. This theoretical clumping has direct and challenging implications for our observational search. Consider the method of X-ray absorption lines. When we observe a distant quasar, we are measuring the average absorption along a single, pencil-thin line of sight. If the WHIM is uniformly distributed, that line of sight will give us a reliable measurement of its density. But if the WHIM is a patchy, clumpy collection of cloudlets, our single measurement becomes a game of chance. One line of sight might pierce a dense knot, giving us a very strong absorption line and leading us to overestimate the overall density of the filament. Another, nearly identical line of sight just a tiny angle away might pass mostly through the hot, diffuse gas, missing the clumps entirely and yielding a much weaker signal or even no detection at all. This could be a major reason why our detections of highly ionized oxygen have been so frustratingly inconsistent. We're not just looking through a smooth veil, but a frothy, magnetically structured mist, and whether we see it depends entirely on the luck of our astronomical draw. The influence of magnetic fields extends beyond absorption to the faint emission we hope to one day detect. If the WHIM were smooth, its X-ray or extreme ultraviolet emission would also be a gentle, uniform glow, which, while faint, would be easier to map statistically. However, if the gas is clumped, its emission becomes concentrated into these brighter, but much smaller and more isolated knots. This makes the overall signal even more challenging to separate from the background, like trying to spot a handful of faint, scattered fireflies from a mile away versus seeing the soft, combined glow of a large, distant city. The magnetic fields, therefore, don't just hide the baryons by making them hot and ionized. They may be further obscuring them by corralling them into a fine, intricate structure that dances just at the edge of our observational capabilities, ensuring that the final portrait of the cosmic web, when we finally achieve it, will be one of stunning complexity. Looking ahead, the final clues in our cosmic investigation won't come from reanalyzing old data, but from a new generation of observatories currently on the drawing boards, instruments so powerful they are poised to transform our search from a game of shadows and whispers into a direct, detailed cartography of the hidden universe. The hunt for the missing baryons is about to enter its most exciting phase yet, driven by our 24th clue: the revolutionary capabilities of future space telescopes and ground-based arrays specifically designed to see the unseen. These are not merely incremental upgrades, they represent a quantum leap in our technological prowess, engineered to target the warm-hot intergalactic medium with a precision and sensitivity that was once the stuff of science fiction. Missions like the Advanced Telescope for High-Energy Astrophysics, or Athena, a flagship X-ray observatory being developed by the European Space Agency, are at the forefront of this new era. Athena's core strength lies in its revolutionary X-ray integral field unit, an instrument that will provide both high-resolution spectroscopy and wide-field imaging simultaneously. Imagine trying to study the chemical composition of a distant, faint cloud with an instrument that can only analyze one tiny pixel at a time. The process would be agonizingly slow. Athena, by contrast, will be like having a million-pixel hyperspectral camera for X-rays. It won't just detect a single, faint absorption line from a quasar. It will spread the light out into an exquisitely detailed spectrum, revealing not just one ion, but a whole suite of them: O-7, O-8, OVI, neon, nitrogen, and iron, all from the same patch of sky in a fraction of the time it takes current telescopes. This leap in spectral resolution is a game-changer for untangling the knotty problems of metallicity and ionization balance that have plagued our mass estimates. By seeing multiple absorption lines from different elements and different ionization states all at once, Athena will act as a built-in diagnostic tool. It will allow astronomers to measure the relative abundances of these elements directly, providing a much more reliable estimate of the gas's metallicity. Furthermore, the precise ratios of these lines serve as a highly sensitive thermometer and barometer for the WHIM. By analyzing them, scientists can pinpoint the temperature and density of the gas with unprecedented accuracy, finally nailing down the ionization corrections needed to convert a line's depth into a firm, reliable number for the total baryonic mass in a filament. Athena's large collecting area, orders of magnitude greater than that of XMM Newton or Chandra, means it will gather X-ray photons at a breathtaking rate, allowing it to perform deep surveys of the sky and obtain high-quality spectra for thousands of quasars, not just a handful of lucky, bright ones. This will let us move from anecdotal detections to a true statistical census, mapping the distribution and physical conditions of the WHIM across cosmic time and definitively weighing its contribution to the universal budget. Complementing Athena's wide-field prowess in the X-ray is the vision for LINX, a concept for a flagship X-ray telescope from NASA with a primary goal of achieving even higher angular resolution. If Athena is the ultimate wide-angle survey camera, LINX would be the most powerful telephoto lens ever built for the high-energy universe. Its resolution would be so sharp it could potentially distinguish the faint, diffuse emission of a nearby cosmic filament from the brighter background, moving us from the realm of absorption studies alone into the domain of direct imaging. While still incredibly challenging, LINX's vision is to see the cosmic web not just as a shadow, but as a faintly glowing structure in its own right. It would peer into the hearts of galaxy groups with stunning clarity, weighing the intragroup medium with precision and observing how AGN feedback directly injects energy and metals into the circumgalactic medium, tracing the Baryons from their galactic origins to their final resting place in the web. Together, Athena and LINX represent a powerful one-two punch for X-ray astronomy, offering both the wide-field statistical power and the razor-sharp detail needed to construct a complete and dynamic picture of the hot universe. But the revolution isn't confined to the high-energy realm. On the ground, an equally ambitious project is taking shape, the Square Kilometre Array, or SCAR. This is not a single dish but a vast network of thousands of radio antennae spread across South Africa and Australia, designed to function as a single, colossal telescope with a total collecting area of, as the name suggests, 1 square kilometre. The SKA's contribution to the missing Baryon problem will be twofold, and both are transformative. First, its sheer sensitivity will make it the ultimate fast radio burst hunter. Current telescopes detect these mysterious bursts by the dozens. The SKA is expected to find them by the thousands and eventually by the millions. Each one of these millisecond flashes, as we've learned, acts as a perfectly calibrated probe of the electron content along its path. With a vast and growing web of FRB dispersion measures crisscrossing the entire cosmos, the SKA will allow us to build a three-dimensional tomographic map of the WHIM distribution. We will no longer be limited to a few lines of sight. We will have thousands, creating a dense, pointillistic picture of the cosmic web's electron density, directly weighing the baryons in a way that is independent of the complex atomic physics that complicates X-ray measurements. The SKA's second major role will be in mapping the cosmic web through the power of hydrogen. While most of the hydrogen in the WHIM is ionized, the cooler, denser clumps and the outskirts of filaments still contain vast reservoirs of neutral hydrogen. This gas emits a faint but specific radio signal at a wavelength of 21 centimeters. The SCAR, with its unmatched sensitivity to this emission, will conduct the largest galaxy redshift survey ever conceived, mapping the positions of billions of galaxies across most of the observable universe. This will provide the most detailed chart of the cosmic web's dark matter skeleton ever created, the ultimate Map-A for cross-correlation studies. When combined with the SZ maps from the next generation of CMB telescopes and the X-ray data from Athena, this will give us an exquisitely precise picture of how the luminous galaxies, the dark matter, and the warm hot gas all intertwine to form the large-scale structure of the cosmos. These future observatories don't just represent new tools, they represent a new paradigm. They are the culmination of decades of theoretical work and technological innovation, built with the explicit goal of solving the very mystery we've been exploring. With their launch and construction, the final veil over the hidden half of the ordinary universe will be lifted, transforming our understanding from a compelling detective story into a detailed and definitive map of creation's complete material reality. We've followed the trail of clues across the electromagnetic spectrum, from the faint shadows in X-ray light to the ghostly imprints on the cosmic microwave background, from the statistical whispers of stacked data to the brilliant chirps of fast radio bursts. Each piece of evidence on its own might feel like a faint, uncertain signal, a maybe or a perhaps, But science, at its best, isn't about finding a single, undeniable eureka moment. It's about the powerful convergence of independent lines of inquiry, all pointing toward the same inescapable conclusion. And that is our 25th and final clue, the overwhelming collective weight of the evidence. When you step back and look at the entire tapestry woven from these 24 threads, a stunningly clear and consistent picture emerges. The missing Baryons are not lost, they have been found. They reside in the warm, hot intergalactic medium woven into the vast, intricate architecture of the cosmic web. Think of this investigation like a courtroom drama. You don't convict a suspect based on one piece of circumstantial evidence. But what if you have an eyewitness, a fingerprint, a motive, DNA at the scene, and a recorded confession? The sheer number of independent accounts, all corroborating the same story, makes the verdict undeniable. This is precisely the situation we find ourselves in with the missing Baryons. The theoretical models, our sophisticated computer simulations of the universe, have long predicted that gravity would pull ordinary matter into the filamentary web and that violent processes would heat it to million-degree temperatures. This was the prosecution's opening argument. Then, the witnesses began to take the stand. The Sunyaev-Zeldovich effect provided testimony about the pervasive pressure of hot electrons. X-ray absorption lines from highly ionized oxygen gave us a direct chemical fingerprint, placing the defendant at the scene of the crime. The Lyman alpha forest showed us the cooler clouds that must be embedded within a much hotter, pressurizing environment. Then, even more modern witnesses arrived. Fast radio bursts delivered their clean, direct measurements of the total electron count across billions of light years. The careful stacking of thousands of faint signals revealed the hidden pattern, the statistical voice of the web speaking in unison. And the cross-correlation techniques showed us that the faint shadows and glows we detect are not random. They align perfectly with the known map of the cosmic web traced by galaxies. Every single one of these methods is fundamentally different. They rely on different physical principles, observe different wavelengths of light, and are subject to completely different sets of potential errors and uncertainties. The X-ray astronomer worrying about metallicity corrections has an entirely separate set of problems from the radio astronomer calibrating the dispersion of a fast radio burst. Yet all of them, when they analyze their data, keep arriving at the same answer. There is a massive amount of hot, diffuse, ionized plasma filling the space between galaxies. This is why no single definitive smoking gun detection was ever likely. The WHIM is not a solid object you can point a telescope at and see a crisp image. It is the most diffuse stuff in the universe, a wispy, ethereal fog that permeates everything. Trying to observe it is like trying to see the shape of the wind. You can't see the wind itself, but you can see the leaves it rustles, the waves it whips up on the water, and the pressure it exerts on your skin. Our 25 clues are all different ways of seeing the effects of this cosmic wind. One method might be sensitive to the very hottest parts of a filament, while another picks up the warmer strands. One might work best for nearby structures, while another can probe the distant, early universe. The fact that they all point to the same reservoir of matter, with a collective mass that adds up to the missing 50%, is the most powerful evidence we can possibly have. The case is no longer based on a single, shaky piece of data. It's built on a robust, interdisciplinary foundation that is incredibly difficult to refute. So, where does this leave the great cosmic mystery? We are now at the point of moving from discovery to precision. The question has shifted from where are the missing Baryons to exactly how are they distributed? What is their detailed temperature structure? How do they flow and evolve over cosmic time? We have solved the puzzle of location, but now begins the even more exciting chapter of understanding the physics of this hidden realm. The convergence of evidence doesn't mark an end, but a magnificent new beginning. It validates decades of theoretical work and astronomical ingenuity, proving that our models of the universe's structure are fundamentally correct, the cosmic ledger, once showing a baffling shortfall, is now being balanced. The grand tapestry of the universe is complete, and we now know that the empty spaces between the stars were never empty at all, but filled with the brilliant, hot, and ever-present substance of creation itself. We've journeyed together through 25 compelling clues in the greatest cosmic missing persons case of all time, the search for half the ordinary matter in the universe. From the cosmic ledger of the Big Bang's afterglow to the subtle shadows cast in the light of distant quasars, from the ghostly pressure imprints on the ancient microwave background to the brilliant chirps of fast radio bursts echoing across the void, each piece of evidence has drawn us closer to a stunning conclusion. The case is no longer one of pure mystery, but of magnificent confirmation. The missing Baryons are not truly missing. They have been hiding in plain sight, woven into the hot, diffuse filaments of the warm, hot intergalactic medium, the very fabric of the cosmic web that connects all galaxies in a vast, invisible architecture. This discovery doesn't just solve a puzzle, it completes our fundamental picture of what the universe is made of, revealing that the space between the stars and galaxies is not an empty stage, but the main character in the story of cosmic structure. Yet, even as we celebrate this monumental achievement, the detective work is far from over. Finding the suspect is one thing, understanding their motives, their behavior, and their role in the larger story is the next great challenge. We've moved from asking, "Where are they?" to a whole new set of compelling questions. How exactly is this vast reservoir of hot gas distributed? Is it a smooth, uniform fog, or is it a turbulent, clumpy medium, twisted by unseen magnetic fields and shattered by ancient galactic winds? How does it flow and circulate? Is there a great cosmic weather pattern, with winds and currents moving between the voids and the dense clusters? And perhaps most importantly, how has this web evolved over the 13.8 billion-year history of the universe? We now have the outline of the map, but the fine details, the topography, the climate, the very metabolism of the cosmic ecosystem are still coming into focus. This is the new frontier, and it's every bit as exciting as the original search. The solution to this mystery does more than just fill a gap in a textbook. It completes our understanding of the ordinary matter that forms the bedrock of reality. For decades, cosmologists have had a beautifully precise model of the universe's composition: dark energy, dark matter, and a small but crucial sliver of ordinary baryonic stuff. But that sliver was only half accounted for, creating a persistent, nagging doubt. Could there be something fundamentally wrong with our core theories? By finally locating and confirming this hidden half, we are validating the entire edifice of modern cosmology. The predictions of the Big Bang model, the readings from the cosmic microwave background, and the simulations of structure formation were all correct. The universe has been playing fair with us all along. We just needed to develop the tools and the cleverness to see the whole board. This is a profound testament to the power of human curiosity and ingenuity, showing that even when the universe hides its secrets in the most extreme and elusive conditions, we can, with patience and brilliance, bring them into the light. But the ultimate prize is even grander. By fully characterizing the warm, hot intergalactic medium, we are not just weighing a hidden mass, we are revealing the full architecture of the cosmic web. This isn't an abstract concept, it is the true skeleton of the cosmos, the framework upon which galaxies are built and the medium through which they grow and evolve. Understanding the web's properties will unlock secrets of galactic evolution, showing us how galaxies receive their fuel and how they interact with their environment. It will illuminate the role of the most violent cosmic engines, supernova and supermassive black holes, in shaping the large-scale structure of everything we see. The cosmic web is the universe's circulatory system, and we are finally learning how its veins and arteries function. This knowledge will transform our view from a universe of isolated islands to a dynamic, interconnected cosmic metropolis where every galaxy, including our own Milky Way, is a participant in a vast, flowing, and ever-changing network of matter and energy. The case of the missing Baryons is closing, but in its place, an entirely new and even more thrilling chapter in our exploration of the cosmos.